Okay. Bismillahirrahmanirrahim. Wassalatu wassalamu ala sayyidil mursaleen wa ala alihi wa sahbihi ajma'in. Distinguished speakers, dear colleagues, ladies and gentlemen, welcome to this workshop, Produced Water Challenges and Opportunities. Produced water is a water trap in underground formation that is brought to the surface during oil and gas exploration and production. The physical and chemical properties of produced water vary considerably depending on the geographic location of the field, among other things. Produced water is by far the largest volume byproduct stream associated with oil and gas exploration and production. Approximately 24 billion barrels of produced water are generated each year in the United States. This is published number. In Saudi Arabia, I could not find a published number, but it is approximately 3 barrels of produced water to 1 barrel of oil. The cost of managing produced water is a significant factor in the profitability of oil and gas production. The total cost can go up to $5 per barrel. The way I see produced water is that it is a challenge, but at the same time, it is an opportunity that can convert all producing companies from net water consumer to be a net water producer. Today, we have distinguished speakers to talk about different aspects related to produced water. Dr. Mohammed Bilad will talk about membrane process and material development for produced water. Dr. Tzhani Cath will address the research gap and advanced processes for treatment and reuse of produced water. And then last but not least, Dr. Shadi Hasan will talk about membranes for produced water. The first talk will be delivered by Dr. Mohammed Bilad. Dr. Mohammed Bilad is an associate professor at the Faculty of Integrated Technologies, University Brunei, Darussalam. He has a strong research portfolio on membrane science and technology as demonstrated by research funding and output, more than 200 ISI journal papers. The good track records have been developed throughout experience working at University of Technology Malaysia, KU Leuven, Belgium, Masdar Institute, and NTU Singapore. He completed his PhD from KU Leuven on membrane fouling control under the supervision of Professor Ivo Van Kilcom. He had also been mentored by Professor Tony Fain when working in NTU. His current research focuses are on membrane technology for water and wastewater treatment, CO2 separation, and bioresource management. He works on ultra-low pressure filtration system for point-of-use membrane processes. He also develops sustainable membrane-based materials and processes. In addition, he is exploring Internet of Things via big data analysis for membrane plan optimization. Another thrust of his research is on development of novel membrane reactors custom to specific challenges. Dr. Mohammed, thank you for being with us. The floor is yours. I forgot to mention and to thank basically Dr. Dahiru for organizing this workshop, and for our dear audience, if you have any question, you can write your question in the chat box, or if it is necessary to talk, you can raise your hand. Thank you very much. Dr. Mohammed.
Can you see my screen?
Yes.
Okay.
Can you put it on? Yes. Thank you.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good evening, I think, in Dahran. First of all, thank you so much for having me here. I'm very glad to share my research works and my future research on produced water treatment using membranes. I managed to compile data of my, I think, last 2 years research, and it is actually the material of my presentation taken from 8 research papers that published last 2 years. Before I start my talk, I want to acknowledge the student that actively involved helping me doing this research. The one on the left, they are postgraduate student helping the one on the right. They were the undergraduate student actually working on this project. I have a few works beyond what I'm presenting this time, but I don't think we have enough time to put all of them together. Briefly before I start, actually, when you start with membrane, you will be dragged to work on many things. My background, my training was on membrane bioreactor actually, but then it spin off to membrane fabrication. Most of my work, they are on membrane fouling, especially on optimization of the aeration for fouling control and hydrodynamics. These 2 topics I will present as well during my talk. Then there are other things that I have been working on, process intensification involving membrane. I also work on new application of membranes, like for heat recovery, membrane oxygenator, I call it here, membrane as mixer, membrane adsorption, and many other things. So my work on membrane and my love on membrane is beyond membrane for produced water. So and the application is for many, as you can see from here. But the topic of my talk will touch about membrane fabrication and membrane fouling control for produced water treatment. This is the outline of my talk. So first of all, I will talk very general on the context of produced water treatment and how membrane processes fit into the big picture, the big process. I will highlight the overview of the produced water treatment and the challenges associated with membrane processes that have been proposed, used, developed, research for produced water treatment. Then I will go a little bit detail on the research that I have been doing on membrane process, in particular for membrane fouling control for produced water treatment, and lastly on development of membrane materials. Okay, if you look into the overview of the produced water, I have an opportunity to have engage in this topic when I work in University Technology Petronas. We work closely with Petronas and then try to help them to solve some of the problems, including the produced water. So during that time, I understand a little bit of the produced water in context. So I'll try to share it a little bit here, very general. So when we produce oil or gas, crude oil or natural gas, we will have a 3 phase. Basically, we'll have gas, oil, and water, and these 3 will be separated in 3 phase separator. Okay, a 3 phase separator. It basically the aim is to separate gas fraction, oil fraction, gas fraction, oil fraction, and water fraction. So the first produced water is coming from this 3-way separator, which is the produced water. So you can imagine that this 3-way separator is on the oil production platform. So you produce, after that you produce, for example, you produce oil, and then oil will be transported into through the pipeline. Sorry. I have a battery issue.
Did we lose him?
Yeah, I think I lost him, but maybe he will join soon.
I thought that this is my computer. Okay. Maybe we will take a break for 5 minutes. Take a break for 5 minutes until we fix the issue with him.
Okay. He's coming back.
I'm coming. Okay.
Okay, all right.
Sorry. Some technical issue.
That's okay.
Okay. So I continue. So this is an overview of how the produced water generated. Yeah. So we initially have the water phase during the three-way separation. So that's produced water. It is in the normally on the oil platform. Then the oil fraction will be piped to the terminal somewhere onshore. So from this stream as well, it contains a minor component of water. And then in the crude oil terminal, then we also have produced water over there. So we have to deal with this one. In the gas terminal as well, through the pipeline, some of the water contained in the stream will condense. And it also generate a fraction of produced water as well. So all of this produced water, so there are three types I specify here. They all produce water, termed as produced water. So if you look into how the industry deal with this one, the produced water, is that first of all, we have to look into what is inside. So it contains suspended oil. You can see the black color of the water in the feed. We have emulsified oil in a form of stable emulsion here, where surfactant help to stabilize the oil water emulsion. Many really depend on case by case. It can have a very high salinity. It can contain metals, toxic even, like boron, cyanida, organics, including phenols, suspended solid, and also sand particle. So sand particle rarely mentioned, but as you have the old well, they generate more sand particle that actually hard to separate. If we go into the processing, so normally we'll have the sanding, where they basically want to, this is using a hydrocyclone to separate the solid fraction. So sand will be removed here. Then the oiling, where the suspended oil will be removed. It can be done using one or multiple processes. Most importantly, I think the hydrocyclone, then tilted separator here, also dissolve air flotation. Okay, up to this point, then it's really, if you can add, so with another process, this is the tertiary treatment. So the need of tertiary treatment is affected by what we plan on the treated water. Will it for reuse, for example, for hydrofracturing, for process irrigation, and or will it for discharge? So we need to somehow develop the processes here to meet the criteria for this purposes. And the tertiary treatments depend on really the use of the treated water and the regulation for such purpose. And membrane process normally will fall into part of the tertiary treatment, okay? Part of this one. This is how to see the context. And if you look into the criteria, so as I said in this slide, what membrane process we need will really depend on the feed that we have, the performance of the oiling here, as well as what we want to achieve in the end. How are we going to deal with the treated water? For example, I don't know exactly, but in Malaysia, for example, if we want to discharge offshore, we need to have treated water that contains less than 30 ppm of oil. Current process doesn't really need tertiary treatment. With descending and de-oiling, we'll be able to meet 30 ppm. Most notably, I think the last process will be using dissolved air flotation. But in another country, including in Malaysia, not in Brunei, but in Malaysia, I know, they're trying to push a little bit hard to achieve oil concentration of below 10 ppm. To achieve this one, they might be require the tertiary treatment using membrane process. Okay, if you want to discharge onshore, like for example in the gas terminal or in the oil terminal, it has to follow the standard regulation of the wastewater discharge. So from that, we can imagine what processes required in the tertiary treatment. For example, here, if we want to reuse the treated water for hydrofracturing, then we need to minimize the solid, the microbe, iron, and anything that can form flux, boron. If we want to use for processed water, then we have to think about what tertiary treatment that required. I make it's a heavy summary of membrane processes that have been reported for produced water treatment. First of all, I think the one that will be mostly used is microfiltration and ultrafiltration. The main function of this process, they are very effective in removing the oil water emulsion. Okay, and they will definitely be required if in the end we want to apply nanofiltration or reverse osmosis. Okay, and I think in the future, ultrafiltration and microfiltration will be largely used for offshore discharge, specifically to lower the oil concentration below 10 ppm. But the main issue for this process is membrane fouling, and after a few slides, I will talk in detail about how we can manage membrane fouling for treating oil and water emulsion. The other process that can be used is nanofiltration and reverse osmosis. Basically, they are highly selective to water, so almost everything will be rejected if we apply this process. It will be placed somewhere at the end of the process to remove the salt, minor organics, maybe if organics required. So we will need nanofiltration or reverse osmosis if we want to reuse our treated water for process. But we'll have an issue. I think the main issue is pre-treatment. I know many of offshore even platform. They also employ reverse osmosis and face a lot of problem with fouling due to the poor pre-treatment performance. So the issue here I list also on membrane fouling. I know some center in Middle East, like 5 years ago. I met the guy who developed the research. They actually tried to implement membrane bioreactors as one of the tertiary treatment process for produced water. The aim is to remove organics, definitely. But the issue will be really depend on case by case. If we have a high salinity, then it will be very hard to cultivate microorganism to grow well, to form a solid good flock. membrane fouling will be an issue. Most of the produced water will also have some of the toxic organics, phenolic compound. So cultivating microorganism will be quite a challenge when we apply membrane bioreactors. Recently, a lot of report on fault osmosis. As they see the treatment of produced water is a sweet spot for the fault osmosis, but then I think the issue will be on a drought solution recovery. How can we run a fault osmosis in as efficient energy as possible? Also, fault osmosis is relatively new. I think last 5 years. I think I don't see any big installation yet applying the fault osmosis. And lastly, membrane distillation. Membrane distillation is basically we produce pure water. The issue there is to develop membrane that is hydrophobic and oleophobic at the same time. That will be a little bit challenging. I hope Shadi will explain this one later on, because when you have a mixture of oil and water, and typically membrane distillation require a hydrophobic membrane, so water will not stick on the surface, but now you will have an oil, so that will be a little bit challenging. The issue will still be high energy input. I know people always claim membrane distillation as energy efficient, but it's the same. So it's the same as evaporation, for example. We will still need an energy to supply the latent heat, although it's at lower temperature. Okay, so some researcher will rebrand membrane distillation as one of the energy promising technology, but I'm not very convinced with that. Okay, so that's basically all of my introduction. So you will see of how the context of the research I have been doing. So it's point 4 and 5 fit well with the overall layout of the implementation of membrane process for produced water. So process development here I define as actually more on dealing with membrane fouling. So the membrane fouling on the first application, which is pressure-driven microfiltration and ultrafiltration, and also I have few slides on actually sustainable fault osmosis. Yeah, so these are the things because whatever membrane we want to deal with later on, I don't think fault osmosis can handle high oil content. Definitely nanofiltration and reverse osmosis will require ultrafiltration or microfiltration treatment. So membrane fouling control when dealing with oil and water emulsion become highly important. I will present 4 different studies with the same approach for tackling the issue of membrane fouling in treatment of oil and water emulsion. First of all, maybe not all of the audience are familiar with membrane fouling. So membrane fouling is basically the loss of performance of your membrane over time. Okay, it reflected by 2 things. By mainly its permeability. So your permeability decrease over time, but membrane can be operated as in a constant pressure. So you apply the same pressure all of the time, and then as function of time, your flux declines. But we can also operate it at a constant flux, and then as a function of time, the pressure required to achieve that flux increase. So I make a very simple simulation here. So you can imagine that when you start the operation, all of the pores are available. So you don't need a very high pressure to achieve the design flux. but as function of time. So when when foulant start to stick on the membrane surface, so now you have less available pore to perform the filtration, and to achieve the same flux, you need to compensate by increasing the pressure. So you see here, and then as the time progresses, then more pore will be blocked, and then less pore available for the filtration. So the pressure increase at a higher speed until a point where actually you say that, okay, we cannot work beyond this one, we have to do some cleaning. So the main consequences of membrane fouling is that we need to operate the membrane in a complex way. Okay, it consists of operation cycles. Here I give, I don't know, 1, 2, 3 cycles involved in it. The filtration, for example, we cannot do to accommodate the fouling control. We cannot do continuous filtration, but instead we apply backwash and relaxation at certain interval. Okay, normally around 10 to 30 minutes. It can be slightly beyond this one, depending on the guideline of the membrane supplier. So we have a filtration cycle. Then above that, we also have maintenance cleaning cycle, where low dose of chemicals, cleaning chemicals, is introduced to further to achieve a better cleaning. So the interval of this cleaning can be from 1 to 2 weeks. It really depend. It will depend on the operation and the criteria of the cleaning. And then once or twice a year, we'll need to do intensive chemical cleanings to restore the membrane performance that lost due to membrane fouling. Okay, so if you try to visualize what the pressure will look like, you will see the pressure goes up, down. So here involve I hope you can see it. So this one involve the filtration cycle, and then you do the maintenance cleaning. So the filtration cycle, maintenance cleaning, filtration cycle, maintenance cleaning, and at one point we decide to go for intensive cleaning, and then we repeat the cycle again until at one point you develop what we call as irrecoverable fouling, that we couldn't restore from the cleaning. So in the end, so as time pass, we'll have to replace the membrane because the performance too far from the original. So membrane fouling then make the process quite complicated and require intense monitoring. So one of the I think the current effective way to do this one is by implementing the aeration. This one probably not necessarily applicable to produced water, but it is an example of lead MBR aeration system technology patented by Tzhani. You can see that they use fast flow of air to vibrate the hollow fiber and clean everything pollen that sticks on. Okay. But the general approach for dealing with membrane fouling, there are so many, and I think I try to make a simplification here by classifying them into 3. We can play with the feed. We can do some pre-treatment. So we'll have a feed that has a low fouling propensity. Some floculations can be dosed here. Probably not really relevant to produced water here. Can also develop membranes that resistant to fouling. Can improve the structure of the membrane. We can fine-tune the surface chemistry of the membrane so that it is more resistant to membrane fouling. And the last approach, I think, more operational, is to deal with hydrodynamics. We try to induce local mixing near the membrane surface by manipulating the cross-flow velocity or flow of fluid around the membrane surface, introducing air bubbles, as you can see from the video I saw here, and some of with the module development. So these are the approaches that can be used, and the part that I want to talk later on is more on the hydrodynamics, how we can manipulate the hydrodynamic near the membrane surface. And yeah, another thing is on membrane development. So the first is that we develop new models. We call it fin spacer. So basically, for the conventional membrane panel, we have vertical plate and frame like this one. And then we, if we go for air bubble for membrane cleaning, so the air bubble will tend to move in the center. I have a short video here. I hope you can see it. If you have air bubbles, it tends to actually move away from the membrane surface. So it's bubbling. The conventional bubbling has very poor efficiency. Okay, you generate a lot of bubbles, but actually the bubble doesn't move nearby the membrane surface. Actually, it's moved as far as possible from the membrane surface. And thus the aeration should be optimized. So what we have developed in our groups is, you see here, this is a video of the system. So we developed a spacer that look like fins that help to direct the air bubbles to the membrane surface. You see here that most of the bubble go to the left side. So when the direction when we want to bubble to move, and then really move close to the membrane surface for cleaning. And then the system, okay, and at this video, you can see if we switch to different side, and actually the system was equipped with a panel that can switch from left to right. Okay, so the spacer here, the function of spacer here is mainly to direct the bubble, the air bubble, so that it move close to the membrane surface and do the cleaning. In three of the studies I present later on, we use a lab-made PVDF membrane with a pore size close to 0.1, some main flow pore size here, and then the oil emulsion, oil water emulsion that we get from the produced water, they have a size of about 200 nanometers. So around there are three models. 200 nano is about, this one is about 800, and it's about 4 micron, 0.8 micron. So in most cases, the oil rejection was very high. So I will not report it here. So the use of ultrafiltration or microfiltration will provide a very good rejection of oil in emulsion. And for this fin spacer, you see here that we managed to increase the steady state flux by almost double, by 86%. And as you expect, if the membrane that is projected with the aeration can offer up to 400 liters per square meter per hour per bar of the permeability, and less so for the non-projected side. And here we look into how many fins that we can install. So maybe you can see that as the more the fins, the higher the flux, so the shorter distance. So basically we can see here illustration here. If we have more fins, then we can keep the bubble close to the membrane surface when we compare it to the larger fin gaps. And we have a CFD simulation, try to visualize what's happening. You can see here that actually the movement of the bubbles near the on the left side is the membrane surface. And actually, we can see there's a counterflow that that on the another side that assists the circulation of the liquid. So it's not only the contact of air bubbles to the membrane surface that plays the roles, but also the secondary flow of liquid on the other side to ensure the fluid circulation. Later on, I will share my slide. If you want to know in detail, then you can refer to the publication here. So another approach that we are working on is on, you see that many people try to develop corrugated membranes or patterned membrane. And when they do that, they have to compensate on other membrane properties. Okay, other membrane properties. The aim for the surface corrugation is basically to enhance the local mixing and also increase the surface area of the membrane. So we have different idea. So we say that why don't we just go ahead with the flat membrane that normally people use? You can buy it even. But instead of having a flat arrangement, so a flat membrane, we can make it wavy flow channel like this one. We make it wavy like this one. We try to simulate what happened through the flow. And you see here, we induce a lot of swirling effect. And basically we can bend the liquid inside here. So the act of bending will improve the contact of the liquid or flow on the membrane surface. And as we expect, here we have wavy channel that can achieve about 220, I think, permeability. And then the flat one as the reference, we only achieve like 180. And we try as well to estimate the energy consumption. So basically, when we have this type of membrane, then you have a longer path of flow, and the nature of the module actually will affect the pressure drop that eventually will increase the energy. But actually, there are not much energy increment in terms of pressure loss. Okay, so this is the second approach we use by improving the hydrodynamics near the membrane surface. And also, lastly, this is a new result that we have. So you can find even some of the commercial product already they have the rotating membranes, but the implementation of the rotating system is not that easy actually, based on our experience as well. So what we do is that instead of rotating the membrane, so why don't we develop a spacer that can rotate so the membrane is static. And this kind of spacer can be placed in the current established membrane. So we have a plate and frame membrane, and then we can put spacer in between, and then this spacer rotate, and the rotating motion actually consume much less energy. This is an illustration of the system. We've developed a bench scale here. Maybe it's not very visible, but this one, the static one, is where we place our membrane surface, and actually the disc, they're actually the rotating disc that act as a spacer in our lab scale setup. We try to visualize in our experimental. We just use half diameter. This is purely for practical point of view. Then we look into what will be the shear rate, shear stress on the membrane surface, and here is the contour of the flow around the membrane surface using a CFD approach. And then the result was quite convincing. See, we can increase from about 120 for the static system up to 180 if we rotate it at speed of 50 RPM. by the way, this 50 RPM, we can translate it into, we have a quite high RPM because of the small dimension of the setup. In a full scale setup where we have probably 2 meter diameter of disc, we will only require a few RPM to achieve the same linear velocity. And as you expect, if might be expected, if we place the membrane closer to the disc here at 0.5 centimeter, we achieve higher permeability than if we put it a little bit far away. And the energy associated with the rotation was almost very small. So here, the unit here is not in kilowatt hour per cubic meter that is normally put. It is in watt hour. So it's a 0.00 something energy per cubic meter of treated produced water. So it is highly energy efficient. We are trying to publish the work currently. I hope soon you will be able to access the detail online. Okay, the next approach we use is that is fault osmosis. Why we go for this one? Because we are dealing with produced water in a gas terminal, and normally the gas terminal is located in the nearby the seashore. So we have abundant access to the seawater. So what we think about, and then we find out that actually the produced water has quite low salinity. Okay, so we think of using the seawater as the draw solution. You see here maybe many of you are not familiar with FO, so I make an illustration here. So we can use you can use the seawater here as the draw solution to pull water from the feed. So this is the produced water. So this way we'll be able to achieve active separation of water through the osmosis without being worried of how can we recover the draw solution. Because what happened is that on the left side, you see here, I have a video. This is from aquaporin actually. You can see that in the beginning, the volume of the water was quite high. As the time passed, the water is pulled to the draw solution side, and we can concentrate it. We can concentrate it and reduce the volume of the feed water. So you can imagine the same setup for the produced water when the water has the very low, low salinity. So we can simply use the seawater and directly circulate it from the sea. The thing is that wherever you go for, I think Cath will have a lot to say about fault osmosis later on, but it's a low first. The good thing is it's low pressure process. When we set it this way, so the FO will have a very low energy consumption because we don't need to deal with draw solution recovery. The process is highly water selective, so basically will retain almost everything but water. And also I think it's penetrating the market currently, so it's good for the future. But I want to challenge the claim here about it's less fouling, because what happened? So this is the approach that we use. I'll talk a little bit later on. So what happened was that this is a control feed. So basically this is a clean water. So this is the demineralized water. So and then we run demineralized water and produced water in this setup. It's basically for concentration. So we try to see how much we can concentrate. And then you can see here that after some time, the flux becomes zero. So at this point, we achieve basically equal concentration of osmotic pressure. So basically, we cannot achieve beyond this one. But the most telling thing is that if you look into the initial flux, the initial flux of control feed, which is the demineralized water, is much higher than produced water. So this is a good, very strong indication of membrane fouling. So based on this observation, we try to improve the fouling control using for the photosmosis using two simultaneous approach, which is improved aeration and through panel inclination. So what we achieved?
2 minutes, Doctor.
2 minutes. Okay. So what we achieved was you can see a clear improvement on the relative water flux. We can increase by 60% here. And also we can further improve the performance by using panel inclination. Okay, I thought I'm given 45 minutes. Oh yeah, it's 45 minutes. Sorry. So I will not go into detail on my point number 5, but the approach we are using here is to develop phase-inverted membrane by incorporating hydrophilic additive, which is using PEG, PVP, and this one with tannic acid. Yeah, the most challenging part of incorporating hydrophilic additives is actually they try to leach out during the fabrication, so that we don't end up with having membrane with hydrophilic, because your additive leach out, and our solution was to implement the FIPS process, vapor induced phase separation. Actually, we introduced some of the time gaps between the casting and coagulation. Here we use PEG additive. We achieve quite good performance. Okay, as you can see from a flux here, but the issue was that PVDF is semi-crystalline. So you see, as we apply a longer time, then the structure become quite brittle and the mechanical strength was weaker. We tried to then apply a different additive, PVP, but the same issue was that the VP was leached out. And in the final approach, we incorporate another additive, which is tannic acid, and we form a complex of Fe, PVP, and tannic acid, PVP, and Fe here to bind actually the hydrophilic additive and to achieve quite high membrane performance. I will not discuss the last things so this is what we have achieved so far. So through the hydrodynamic enhancement, we can achieve permeability of around 400 here using fin spacer. Okay, using fin spacer here. I'm sorry. Okay, rotary spacer, we can go only up to 150, wavy flow channel around 200. PVDF, PEG, we can have only this amount, PVDF, PVP only this amount. But the last approach, when we combine PVP, tannic acid with complex session chemistry, assembly of tannic acid and PVP, we can achieve close to 300. So I think the two approach, which is to apply fin spacer and develop membrane material with a smart way, hydrophilic membrane material, can offer the good performance. Okay, I move to the last slide. There are to deal with membrane fouling in produced water, we probably need to go with the multi-prong approaches, not only to go with hydrodynamics or to only go with the materials, but we come with the combination of multiple approaches at the same time. Okay, I think that's the best approach. As you can see, I believe that if we can combine this membrane with this process, we can achieve much better performance. This is the plan for the future. Another thing is probably what next with the concentrate. So whenever we have membrane, for example, RO, we have brine. If we are now treating the produced water with high oil water emulsion, oil concentration, then what happened to that? That is one of the untapped research, I think. Another thing is it is about the time to go more holistic or more engineering approach in implementation of membrane processes for produced water. I think that's all from me. The last few slides, I skip it quite fast. I didn't realize I already spent 45 minutes. I think that's all from me. I will welcome questions.
Yeah, thank you very much, Dr. Mohammed. Interesting and informative talk. I guess we have one question, room for one question, and then later maybe we'll have more question at the end. If there is any question.
I have a quick question to Dr. Bilad on the rotating spacer. You know, I'm a practical person, so practically when you will try to commercialize something like that, isn't there a worry that the rotating spacer will scratch the membrane or impact the membrane?
Actually, yeah, that's a good good questions. At this moment, no, because we can actually make our future plan is actually to make the spacer from sponge-like material that actually do the mechanical action to wipe actually the membrane all the time. So we are not really worried about that mechanical failure at this moment, because we know some people do develop the spacer with even a smaller gaps in a millimeter scale. Now we are talking about 0.5 centimeter. So I think that's something can be achieved by the current engineering.
Oh, that's cool.
Yeah, I was thinking about this the other day. Is why not using like sponge balls like those that are used to clean the heat exchanger from inside? Is that a possibility to use those sponge balls and squeeze them, and then it will clean the surface? Is that a possibility?
Well, all of you are very smart already, so you get all what we are doing now. Actually, what we do now is very simple. So we add some sponge on the surface here, and it's like a wiper in the car that's clean it all the time. It works really well, and then we can achieve like double what we achieve now. Yes, that's very true. We are working on that one. We're producing some result already.
All right, excellent. All right, thank you very much, Dr. Mohammed. Very interesting talk.
Yeah.
The next distinguished speaker is Professor Tzhani Cath. Cath is from Colorado School of Mines, USA. He's a professor of environmental science and engineering. His research focuses on membrane separation processes for desalination and for water reclamation, on desalination of concentrated brines for water and mineral recovery, on potable reuse of reclaimed water, on treatment of industrial wastewater, especially in the oil and gas upstream sector, and on the interface between energy and water. Professor Cath has been leading projects that focus on direct potable reuse of water in domestic wastewater treatment plants and in life support systems, treatment and recovery of produced water, and fracturing flowback wastewater from unconventional gas resources, treatment of water in geothermal power plants, zero liquid discharge systems for enhanced desalination of brackish water, development of decision support tools for water reuse, and development of advanced control systems involving early detection of system failure. Professor Cath is the director of the Advanced Water Technology Center and co-director of the WE2ST Center at Mines, and he holds a joint appointment with the National Renewable Energy Laboratory. Dr. Cath, thank you for being with us at this early morning in Colorado. The floor is yours.
Excellent. Thank you so much for inviting me. Very sad that we cannot do it in person, but that's life now. So I couldn't ask for a better introduction than what Dr. Bilad gave. I think, he, prepared very nicely for things that I want to say. I think a lot of what I will talk about is on new research, support in the US for the oil and gas industry. And I think a lot of the focus will be on short treatment trains to treat and reuse produced water. And I, you'll hear me talking about some of the things that Dr. Bilad talked about, but I'll also talk about what's the implications of developing these technologies. Nothing is bulletproof, and nothing is a silver bullet. So, there are always little things that we need to consider. I will also start with acknowledgement of many companies and organizations that support my research. Here at the top is I think I captured most of the students that were involved in things that I will present today. And especially in the oil and gas, we lately had very good collaboration with the Lawrence Berkeley National Lab, and specifically the Joint Genome Institute there, because we are focusing more and more on biological treatment for produced water. Again, also great introduction by Dr. Bilad. So again, I'll talk a few notes about the new National Alliance for Water Innovation, NAWI, in the US, and the road mapping and baselining that we performed. And then I'll talk about treatment and desalination of produced water, and with a focus on pre-treatment, because if we can do pre-treatment, our desalination, again, as Dr. Bilad said, will be much easier to do. And I'll give a few examples from recent and ongoing research. So NAWI is a new center that funded by DOE, led by 4 national labs and many universities and other partners, with a focus to reduce the cost of desalination of unconventional sources of water, including industrial wastewater like produced water. It's a $100 million over 5 years with a focus of TRL 2 to 5. And again, TRL is technology readiness level. So we are stopping before piloting. So this is early stage applied research with 4 topic areas, and specifically material research and development, process innovation, modeling and simulation, and integrated data and analysis. We just finished first year with the main role of the first year to do road mapping, to look at what are the research gap in the different areas of reducing water cost. In year 2 to 5, we will have applied research in universities and a lot of collaboration between university and national labs. So I introduced the different, topic areas, but there are also challenge areas. And now we identify 6 challenge area with the acronym of A prime: autonomous system. How do we operate system remotely? Precision separation with the eye to recover valuable material. Resilient treatment and transport through membrane and through other processes. Integrated, intensified brine management. Again, was mentioned today, when we start desalinating water, we are generating very concentrated brine. What can we do with them? Modular system, we are very familiar with it in the oil and gas. We want things to be modular, move from one wellhead to another. And electrified treatment process, with which I try still to understand what exactly, but it has different heads. It's about how to make processes more electrified, like electrocoagulation, and how to combine renewable energy into operation in the field in remote locations. So this is how the world of NAWI looks like. Here's the challenge areas, the 6 challenge area and the 4 topic area, and all the research will go here towards the goal of 90% of non-traditional water sources achieve pipe parity. And what pipe parity? Pipe parity is how to bring the cost of the next gallon of water, which is usually more expensive, to the current cost of water. And when you look at pipe parity matrix, you can measure pipe parity under different units, like dollar per meter cube, or how many kilowatt per meter cube, or what's the water intensity. You have different measure, and we still collect different matrix for pipe parity, but the main topic is looking at the energy cost and the levelized cost of water. And under all these confusing things, we are focusing on several industries: the power industry, research extraction, where oil and gas is sitting together with mining, other industries, municipal water, to include seawater desalination and brackish water desalination, and agricultural. And again, all of you know that these are really energy and water extensive industries. So now we just finished and published the roadmap, the master roadmap for NAWI. You can go to the web and download it. I was in charge with a colleague from UT Austin, Professor Lynn Cath, on the roadmap for the oil and gas sector, and that's published under the same web page. And you can also download and see. And we recently published a paper on a technology baseline. So what's now existing? What's the cost? We gave a few case study on specific application of technologies for water reuse. And I think one of the things that we focus on in this paper, towards the end of the paper, is the chemical characterization and toxicity challenges of produced water, and looking at future toxicity as a measure of how well we are treating water. Because, as you know, produced water has a lot of contaminants, and especially when it comes to organic contaminants, it's almost impossible to characterize, what exactly is there and how well it's been removed. It's also very expensive to do this analysis. So toxicity can be one of them, and we propose the methods for incorporating adverse outcomes pathways and toxicity analysis of produced water for reuse. So again, I will not read the paper here. You are more than welcome to go and download the paper and look at what we have proposed. So treatment challenges. Again, I will go quickly because Dr. Bilad mentioned many of the things, but a lot of different things. Water is a major component in the oil and gas industry, and the major challenges is the high variability of both quantity and quality of the water, and the high salinity. And when we have high salinity, sometimes some processes are just irrelevant, because I think, again, Dr. Bilad mentioned high osmotic pressure. You cannot use forward osmosis, and I will talk a little bit about forward osmosis too. And there's the other challenge is that we are it's all about the market. Should we reuse the water or just get rid of it? What's more expensive, to treat the water or to secure new water? And different places in the world have different challenges. Some places you want to get rid of the water. Sometimes you really want to reuse water because you don't have other options. So the potential solution that we think about is how to make short treatment processes, because you can imagine every process that you add, and you need to do some processes for pre-treatment, some process for desalination, some post-treatment, it's just becoming more expensive. So if you have a short treatment man with a few processes can do most of the treatment, you save money. Okay, so a few thoughts about the cost of desalination. So seawater reverse osmosis, we all know it's the workhorse. It's thermodynamically, we're there. We cannot improve it much more. And when we do seawater desalination, we cannot do much more than 60% recovery. Again, because of osmotic pressure, and we are starting with around 3.5, which, some produced water are at this level. Some of them are much more concentrated than this. Now, if you look at the cost of seawater desalination today with reverse osmosis, in the US, it's still a little bit expensive. Places like Australia and Israel, they had other ways to do it, and it's much more, much cheaper. And then in the US, in a good day, in a good place, it costs $0.5 per barrel to dispose, deep well injection of produced water. And so when you do the conversion, there are 6.3 barrels in 1 meter cube. It tells you that you need to be much less than 3.5 dollar per meter cube in order to be in order for your process to be better than disposal. So it is a challenge, and it's difficult to figure out how to treat it so that the industry will adopt new technologies. So the basic requirement for treatment, again, it's a multi-barrier approach, pre-treatment, desalination, and sometimes you need post-treatment depending on what you want to do with the water. Irrigation will have different pre-treatment, drinking will be different post-treatment. So we are all familiar with these requirements when you do treatment. There are, when it comes to the desalination process, there are new approaches that people are promoting for desalination of highly saline water, more than seawater, like the closed-circuit desalination, CCDRO, flow reversal, that is sort of competitor to CCDRO. People are pushing very hard on ultra-high pressure RO. We're talking about the 1,000, now 2,000, even 3,000 PSI of pressure. And something similar is the counterflow reverse osmosis that was proposed by Yale University recently. And whatever you look at these processes, pre-treatment is becoming more and more important to remove organic fouling, inorganic scaling, and other problems that you'll have if you will not remove them from the water. So I'll focus a little bit about pre-treatment on pre-treatment. And when you do pre-treatment, you can either use the water, for reuse in the oil and gas field, or we can use advanced processes after that and desalination, as I just mentioned, to make the water even for high quality for advanced reuse. So pre-treatment, we can do different types of pre-treatment. We can do physical processes like phase separations, stripping of volatiles, filtration, membrane, like osmosis. We can do chemical processes like coagulation, adsorption, oxidation, disinfection. There are different things. And again, we need to combine them sometime together. And for pre-treatment of most wastewater, you can also do biological processes. And I am not a microbiologist, but I think it's a fascinating area if we can convince microorganisms or select microorganisms to do what we want to do. And we can do it in activated sludge processes, in membrane bioreactor, or biologically active filters. And I'll show some interesting results. The problem is, of course, the impact, temperatures and chemicals on microorganisms, and the impact of loading rates, so how much organics or other contaminants you put, and the post-treatment that needed for this water. And of course, the changes in characteristic of biosolids in the bioreactor, or what do we do with these residuals when we are done with the process. So I'll dive into some examples of processes and technologies that we are testing at School of Mines. And Dr. Bilad will have to forgive me because I'll say some bad things about forward osmosis. I made my career on forward osmosis. I think it's a fascinating process, and I think there are a lot of questions where this process will go. But I'll start with early days when I started working on produced water. We developed decision support tools to select technology for produced water treatment. This tool is still available. We later on developed a second tool that incorporated many processes, many water qualities. And I like to give this example from one of my students that, a Rubik cube have 8 corners, 12 edges, and therefore more than 3 billion combinations. And so when you have a decision support tool to select treatment processes in a treatment train, and you have 32 processes and 46 water quality parameters, you have many billions, if not trillions or more of combination, and you have to select what are really legitimate and logical trains. And so we published 2 papers with case studies on that, and again, available to you. But the unique thing is that now we develop a new tool based on these development, and it's called WaterTap 3. And that's a fully developed tool with both the water quality side and the more on the techno-economic part of selecting these processes with, you see, the pipe parity parameters. Okay, I'll go to membrane to forward osmosis, because that's that's where I started my academic career. And you all know osmosis. You put water across a semi-permeable membrane, and the process will stop when the delta P equals delta pi, pi dropped here, and the people, so it's not sustainable, and so that's what we're. But it was implemented in the field, and people develop what's called forward osmosis or engineered osmosis, where you combine the osmosis with a reconcentration process. You reconstitute the draw solution, and you can continue draw water from the feed. And so we received small funding from DOE to test forward osmosis for produced water. And we built a small pilot system of forward osmosis and reverse osmosis. And we tested it with real produced water. And so what we discover is that after a while, regardless of the feed concentration of dissolved organic carbon, you get really consistent water going through coming out of, after the forward osmosis and reverse osmosis. Again, we use reverse osmosis for reconcentration of the draw solution. And you can imagine our produced water was between the 20 to 40 grams per liter salinity. So forward osmosis worked really great. But you can see that even after two barriers, seawater reverse osmosis and forward osmosis membrane, still you have high concentration of dissolved organic carbon in the final permeate. Sorry, that was the RO feed, that's the draw solution, but we still had high concentration of organics in the permeate. What you do see is some of the organics that we are really concerned with. We couldn't find them, after the forward osmosis, so very high rejection of forward osmosis, and the forward osmosis with the reverse osmosis, even better performance, up to 99% rejection of these contaminants. But this is the unintended consequences. Over time, as we did analysis with the sophisticated analytical tool like liquid chromatography, we discover a few compounds in the permeate or final permeate that we didn't know what they are. And after a long search, we found that these are components of ingredients in the production of membrane, which means that forward osmosis is a pre-treatment, and I look at forward osmosis as a pre-treatment for desalination. When you have interaction between different chemicals in produced water, and polymers are relatives, are family members of oil and gas, then you can slowly dissolve component of the membrane and eventually lose the integrity of the membrane. So something to think when we develop membrane is what is the reactions between membranes and components of produced water. And of course, as Professor Bilad mentioned, we use produced water without pre-treatment, again, just other than gravity separation. And you can see how the forward osmosis membrane looked like after 3 months of operation and some attempt of cleaning. Which means that, for forward osmosis, you'll need a little bit more pre-treatment. Okay, I will jump to another approach that we had, and that's biological processes in biologically active filters ahead of ultrafiltration and then nanofiltration. Again, short treatment train with pre-treatment and desalination. We built some small scale system to produce water and test it with real water from the DJ Basin north of Denver. So starting this process, you have to acclimate the bioreactor. So you can see that we operated the bioreactor with batch operations. So we took a batch of 10 liters, recirculated in the bioreactor, and you can see that over time, slowly the performance is getting better and better. And we got to the point that within 24 hours, we removed more than 90% of the dissolved organic carbon from the water. For the nanofiltration, we compared conventional NF to closed circuit desalination NF. And there are many benefits of doing closed circuit desalination, like higher flux and recovery, lower fouling, less membrane used, and even flux distribution among the membranes. And these are the general results. This is a color code. You know, red is high, green is low. And these are the pre-treatment, and then in the nanofiltration, as you can see, we tested it under different pressures. And of course, as we all know, higher pressure in reverse osmosis or nanofiltration give you higher quality water. And you can see that the DOC went from, you know, close to 400 milligram per liter to less than 2 milligram per liter. And the TDS went from the 15,000 to less than 1,000, almost drinkable water, really high quality water. We also saw the performance of the nanofiltration membrane, including sort of membrane cleaning in the middle and exchange of a batch. And you know, you see flux decline, of course, due to probably fouling, but overall sustainable operation. And again, very low concentration in the permeate of DOC, total nitrogen, and TDS. We also looked at the performance of the membrane. We tested 3 products, NF90, BW30, and EcoPro. It's another product from Dow, today DuPont. Overall, all of them were relatively sustainable and operated very well. We also looked at the rejection of different organic contaminants that you might see in oil and gas, and overall, except for a few very high rejection, and we did not find correlation between the molecular weight of the contaminants and the performance of the membrane. But you know, something interesting happened when we looked at the product water from these processes. We started seeing some what we call disinfection byproducts. We have chloride and bromide and iodide in the water, and we started discovering chlorinated, brominated, iodinated compounds in the water, and in some of them in alarming concentration in the microgram per liter. And you can think about it, when you have these compounds and you have methane in the water, and we eventually also discovered some iodide oxidizing bacteria in this water. This is what can happen. And when we even stored the samples in the refrigerator for 3 months, we actually discovered that the reactions continue, and we actually discovered more of these chlorinated compounds that I think all of you that took environmental chemistry know that some of these are carcinogenic. So low concentration still in the air, not, you know, you don't drinking yet. There are ways to treat it. But again, another thing is that you have to think about when you develop processes, what are the consequences? The last section I want to talk about membrane bioreactors, and as much as we think, you know, so saying we saw good performance of biologically active filters. That was great. Bugs got adapted to it, saying, why won't we go to membrane bioreactors? And there are many advantages to membrane bioreactors. And so we decided to try it, and we built a small MBR for produced water, as you can see here. And we use these coke Puron membranes that have aeration coming from the middle of the bundle, and again, to avoid fouling and scaling on the membrane. And what we did is that we started with water from the DJ basin after we inoculated the bioreactor with just activated sludge from a wastewater treatment plant. And slowly we artificially increased the salinity of the water all the way to 100,000 milligram per liter, or sorry, that's not milligram per liter, that's gram per liter, sorry. Here, quickly, I'll change it. So anyway, so this is high salinity, and the target was 100 because the main basin in the US, the Permian Basin, has produced water of around 100 grams per liter. And what you can see here with the bioreactor, that over almost a year of operation, we brought different batches of water. Again, this decline in the feed water concentration is because of the gradation of the organic matter within the tank, the feed tank. We didn't chill it. But again, regardless of what we're doing, the permeate is really, really of consistent quality as it comes to DOC, very clear water. And you see the average permeate DOC is 10 milligram per liter. We then, at certain point, switched to water. We got a batch of water from the Permian Basin with approximately the same TDS concentration. And you can see that actually here, this water has naturally a lower DOC concentration, but you can see that the DOC in the permeate jumped up, and we are still trying to figure out if it's something, something that the microorganisms don't like in the water, or this is different organics that it's more difficult for them to degrade. So this is still ongoing research to understand why the DOC concentration is higher in the permeate there. We take the water and we run membrane distillation. Also, Dr. Bilad mentioned membrane distillation. It's a nice process, and in this case, we looked at the flux and recovery. So flux in green, see really consistent flux up to 70 to 80% recovery of the water. Again, if we are talking about starting at 100,000 milligram per liter, we are getting close to 180. So very highly concentrated at the temperature of 50 and 30 degrees, 50 feed and 30 permeate. Again, it is still a process that's under development. Fouling can be an issue, but again, if you do a good pre-treatment, you'll be fine.
Cath?
Yeah, I'm two slides from the end. We, again, as I said, working with the Joint Genome Institute at Lawrence Berkeley, looked at the development from activated sludge down into what happened when we operated 100,000 milligram per liter. And you can see that there's a shift in the microorganisms that's doing the work, and you can see here the ones that appear here are merino, so microorganisms that are adapted over millennia and millions of years into these extreme conditions. And if they select for themselves to be there, they will do a good job in bioreactors. We're doing many other studies that, again, we don't have time to talk about on produced water treatment, from irrigation to what to do with the solids and other types of bioreactors. And I'll end the presentation with a study that we're actually doing in collaboration with the U.S. Environmental Protection Agency, looking specifically at the toxicity of water as we go through treatment steps. And we think that toxicity will be a nice measure in the future to how clean the water that we are producing from produced water are. And with that, thank you so much. And I'll be happy to have a question now or later.
Thank you very much, Dr. Cath. Very interesting talk. We have room for one question now, maybe. If you have any question. Okay, Dr. Tzhani.
Yes.
Yeah, go ahead.
Yeah, thank you very much, the presenter, for the excellent presentations. Meanwhile, from the beginning, you mentioned something related to the emerging applications of membrane technology, including computational methods. I was just wondering, is it applicable, computational models and modeling simulations that you mentioned?
Is that question for me or for Dr. Bilad?
Yes, for you, sir.
Yes, I think that there is, again, I'm working also on data science integration, more into the area of early detection of failure, so using statistical models. But what we are doing now is looking at development of what you hear people talking about, digital twin. So it's a model, is a simulation model that runs in parallel to your process. It receives all the time data from your process, calculate, what would be a better point to operate, and send back to the process new operating conditions and new set points that the system run in the new, in the future, sort of from that point and onward. So, and now he's developing a lot of tools now for simulation and modeling. So I think it is important, but eventually it's also important to do the applied research to validate that, whatever the models are saying, it really happens. And finding things that, of course, models cannot find. And probably Dr. Bilad has better things to say about it than me. You're muted.
Not many. Actually, what I see is that we have a lot of full-scale plant now. We have abundant data. We can use that data to study faster using the tools of computer and data processing, I guess. I have a question actually to Dr. Cath. So good. What we experience when we deal with real produced water is that whatever the quality we claim in the end, we can still feel the smell. You can still smell the things in the product. I don't know what it is. Another things might be because you're talking about the membrane degradation. What sort of concentration factor we are talking on? Because I believe that there are organic solvent there in your produced water. So if you concentrate it enough, I believe it will swell or maybe dissolve the membrane material actually.
And absolutely, and these are low molecular weight, volatile organics that will be there. I don't want to gross anybody here, but when I was a graduate student and a postdoc, we did some study for NASA on reclaimed water in space, and we treated urine to recover water from urine from space with membrane distillation, and you get crystal clear water, beautiful water. But you sniff it, you smell urine because of the organic acids that manage to evaporate through these membranes. So I think a lot of it can be solved with, for example, adsorption processes like organic activated carbon, powder or granular or ion exchange processes. But yeah, the problem is with the low molecular weight contaminants.
Okay, thank you very much. Our next speaker is Dr. Shadi Hasan. Dr. Shadi had a technical problem joining us, but I think he's on now, right?
Yes. Can you hear me?
Yes. Yeah, so Dr. Shadi, he's from Khalifa University with a Google Scholar H index of 28. He's an associate professor of chemical engineering and a theme lead of nanomaterials and membranes at the Center for Membranes and Advanced Water Technology at Khalifa University. Dr. Hasan's field of expertise includes desalination, wastewater treatment, and reuse, nanomaterials and membranes, and energy efficiency and sustainability of water processes. Dr. Hasan has worked on the development, characterization, and testing of advanced hybrid membranes for water and wastewater treatment. He has more than 140 journal publications and conference proceedings, 1 patent, 1 book, and 15 book chapters. Dr. Hasan's research has significant impacts and led to several funding opportunities, both internally and externally, totaling up to 7.3 million US dollars. He's also serving as an editorial board member for Canadian Association on Water Quality, International Water Association, International Desalination Association, Global Clean Water Desalination Alliance, H2O minus CO2, Water Process Engineering, Water and Desalination Research, among others. Dr. Hasan has supervised more than 40 master and PhD students and research fellows. He has been recognized among the top 2% scientists by Stanford University in 2020 and 2021. Dr. Shadi, welcome, and thank you for being with us. The floor is yours.
Well, thank you very much, dear Hasan, Dr. Hasan, for this very interesting, long introduction. As indicated by my colleague, Professor Cath. I mean, I couldn't find anyone better than this introduction. So before I get started, I would like to thank KFUPM. I would like to thank you, your team, for the great opportunity, being here with all of you today. I would like to extend my appreciation to the audience who made it, this time, especially if you're attending this workshop, from the Gulf region or even, from Asia. I'll try to wrap things up. I mean, quickly, not to be so long, especially, for my colleague, Dr. Roil. I think it's approaching midnight, over there in, in Malaysia. And by the way, Dr. Roil, it's a pleasure. I mean, seeing you today. We met, I mean, a few years back, at Mazar Institute when Dr. Roil joined our research group. And I'm very glad, I mean, to see you progressing, in your research activities, the work that you've done on the spacers, on the find, I mean, on the MBRs and so on. Like, very, very fascinating. I wish you all the best. Dr. Cath, I'm very honored to be here with you as well. And I listened to your very fascinating talk about, produced water in the market, the economy and so on. And I totally agree with all the speakers, about the importance of produced water treatment, the challenges, raised in this field, the very nice, the endless debatable, let's say, discussions on the applicability of MD and FO. So I think, that will continue until we figure out, I mean, the challenges, or to solve and resolve, all these challenges associated, with these technologies. So without further ado, I mean, so my name is Shadi Hasan. I'm an associate professor at the Department of Chemical Engineering at Khalifa University. In Khalifa, for those who do not
Dr. Shadi,
yes.
Can you put it on presentation mode, and if you wish to open your camera as well, if you want.
It is on the presentation mode. Okay, let me try.
What we see is the presenter mode.
Oh, okay. Let me try again. How about now?
It's still probably,
Same.
it's switched between your screens. Well, maybe
Because in both monitors, I can see it on presentation mode. This is awkward. Okay. Okay, let me see. Let's try that. How about now?
The same.
Still the same.
Maybe click on the display setting on the top.
Someone says change from the slideshow.
Yeah.
Yeah, I think that.
Yeah, it says intro.
No, no. On the top, there is a display settings. I think
Here?
that's.
Yeah, this is what I have, because it's very strange. Unless I disconnect, you know. Let me see if I work from my laptop. Okay. Let's see now.
Oh, excellent.
Yeah, it works.
Here you go.
Great. Because you know my camera is on the other side. That's why it was I don't want to confuse anybody. But let's see. Do you see me clearly? Do you hear me clearly?
Yeah, now it's loud and clear.
All right, excellent. Okay. All right. So as I was saying, I'm at Khalifa University, and Khalifa University, is basically resulted from the new merge, between three institutions in the UAE. That is the Masdar Institute, the Petroleum Institute, as well as the old Khalifa University. So we came together a few years, like 3-4 years ago, and established, the Khalifa University. And before I move forward with my slides, let me see now. Yeah. So before we proceed, into the and dive into the main topic, of this workshop, let me just take you through the CMAT center that we have at Khalifa University, which is basically the Center for Membranes and Advanced Water Technology. It was established back in 2018 with a vision to be a world-leading center with an international collaborative research and development environment, focusing mainly on the UAE needs in general, in particular, and in general on the global water issues. So the mission that we have at this CMAT, what's so-called a CMAT, is basically to undertake, multidisciplinary collaborative research to cover different thematic areas, such as process development for desalination and water treatment, novel membrane development, novel materials and nanomaterials for water applications, thermal desalination processes, as well as water microbiology. In the CMAT, we have, as I said, a multidisciplinary, let's say, platform. So we've got faculty from different departments at Khalifa University, mainly from the chemical engineering department. However, we have colleagues from the mechanical engineering, biomedical engineering, as well as chemistry / biology. We have also, several researchers in terms of research scientists, postdocs, research engineers, research associates, as well as, we have several PhD and master students also, working hand in hand in the CMAT Center. At the CMAT, we have established several projects, both nationally and internationally. For example, and with organizations, as well as, institutions and universities. So here I just listed, a few examples of the joint projects that we have with our partners. We have an advisory board, including, very well established top scholar scientists, in the across the globe. For example, we're very proud to have Professor Drioli, Professor John Leonard, Professor Mouli, as well as several other colleagues, from the United Arab Emirates, sitting, on the advisory board, monitoring the performance of the CMAT Center. And luckily, we have expanded, over the past or since the establishment of the CMAT Center, and we started, working on several projects as well, as I said, both nationally and internationally. So focusing on the UAE needs, and I thought of also, highlighting, the situation of the water history in the United Arab Emirates, in order for most of the audience, those who do not know or do not have any idea about the situation in the UAE in terms of water. So I thought of putting, throwing a few slides on that. So Abu Dhabi or United Arab Emirates, we face water scarcity issues, and our Crown Prince, His Highness Sheikh Mohammed bin Zayed Al Nahyan, once said, water is more important than oil, for the UAE. So basically, they have been investing a lot, putting a lot of efforts, I mean, in tackling this issue, trying to overcome, the challenges associated with water in the UAE. So generally speaking, the United Arab Emirates or the Emirate of Abu Dhabi, we depend solely on three sources in order to get our fresh water. So basically on groundwater and desalination, as well as, we have some percentage, coming, from treated wastewater. As I said, the several challenges that the United Arab Emirates facing, the high cost of water production, high salinity levels in groundwater tables, because we have, some intrusion, of seawater into our groundwater tables, the limited water reuse, the current water reuse percentage, stands at 51, so to speak, currently. With the aim of increasing, as I will explain, in the next few slides, to 95%. So basically, in terms of wastewater treatment or wastewater collection and treatment in general, in the United Arab Emirates, basically, we discharge or we reuse, 51% of that treated wastewater, while discharging, 49% back into the marine environment. And from that 51%, more than 90%, being reused for agricultural purposes. But since the September 2017, the UAE's Ministry of Energy and Industry launched what we call the Water Security Strategy 2036, that will aim at lessen the total demand for water resources by around 21%, raise the water production index to approximately $110 per cubic meter, decrease water scarcity index by nearly 3 degrees, expand the country's water storage capability for up to 2 days, and most importantly, recycling wastewater to 95%. So which implies, or which falls, into several categories, if I'm going to put it in that perspective. Basically, if we want to go, by 2036 from 51% to 95%, so that implies, looking at enhancing water quality, the one that we get from the wastewater treatment plants, in order to allow, for other, let's say, reuse applications aside from agricultural purposes or irrigation purposes. So perhaps we can think of recharging our aquifers. We can think of recycling that water, as a processed water, but as I said, improving the quality is very essential. And when we talk about wastewater, we don't want to exclude, produced water, as we will see later on. So in terms of the global energy market, as of the 2019, the UAE becoming, the top 10 global crude oil producer. It's a member of the OPEC and the GECF, a major oil producer and exporter, producing an average of 4 million barrels per day of petroleum and other liquids, with reserves of nearly 100 billion barrels of crude, and also it becomes the 7th largest natural gas reserves globally at 98 billion barrels, with most of the reserves located in Abu Dhabi, which is about 96% of the UAE's total, when compared to other emirates and cities, in the UAE. So looking at the industrial, let's say, wastewater treatment market, as you can see from this figure, it's going rapidly. It's progressing quite rapidly, over the past few years, and it's expected, to grow in the near future. The amount of water, that is being generated as either produced water from oil and gas exploration or from oil refineries, basically, are huge. So if you look at the produced water, from oil and gas, we say, 3-to-1. So 3 barrels, of water for each, or 1 barrel, of oil, and between 0.4 to 1.6, of water, that is being generated when we refine crude oil. So all in all, we can see a lot of huge volumes, of produced water generated from those industries, and that, should be considered and treating, especially, if you have, let's say, stringent regulations, water regulations, that will leave you no option. That you have to protect the environment. So you need to monitor the water quality that is being, discharged to the marine environment, or if you want to reuse it locally, so you have to consider the stringent regulations, that will be applied on you as an industry. In terms of scientific publications, so as you can see from this figure, the topic of produced water, has been attracting several researchers around the world recently. So you can see also the significant increase in the number of publications, between 2010 to 2019, and I'm sure if you do 2020 and 2021 and 2022 and so on, so you will see even a much more increase, in the number of publications in the topic of produced water or oily wastewater. So we are looking into the same, more or less, the same problem here. So as I said, we have produced water generated, from the oil and gas exploration, and the refinery oil, or the oily wastewater, that is being generated, due to oil refining process. So we don't want to mix up, these two things, although, they have a lot of, let's say, common things, but with slight differences in terms of, let's say, presence. Like, for example, in produced water, you have more organic, dissolved organics, whereas in the refinery produced water, you have more of the inorganic, not dissolved, pollutants. So we need to be careful, when we address each type of these oily wastewater. So once again, I don't want to go through that because thankfully, my colleagues, Professor Cath and Dr. Roil, presented very well, the different treatment processes or the methods, going from primary, secondary, tertiary, and sometimes, polishing these types of wastewater in order, to get, let's say, a sufficient, more or less, or a meeting requirement, type of water quality. These are some of the advanced, treatment also, being considered, such as, if you look at the thermal, some MSF, MED, biological, MBR, Professor Cath, he presented a few studies, on the utilization of MBR in the treatment of produced water. And in that regard, because I think Professor Cath also talked about, the electrified, treatment processes. And he reminded me, with the technology which I have developed, back in time in Montreal, in Canada, during my PhD studies, back then, more than 10 years ago, when we developed, what we call the electro membrane bioreactor. So we incorporated the electric field inside the membrane bioreactor, and we have noticed, or observed significant, enhancement on the overall, let's say, water quality in terms of nutrient removal, significant reduction in membrane fouling, and so on and so forth. So this is perhaps, can be also tackled, as I will show you, at the end of the presentation, if I get more time. I mean, towards then how we incorporated also, advanced oxidation process, in for the treatment of produced water. So also, this is just like a very generic slide, showing the different membrane schemes that we have, going from microfiltration, ultrafiltration, nanofiltration, reverse osmosis. And we all know, membrane technology depends on size exclusion, in addition to other, let's say, rejection mechanisms. So this is where, we believe that membrane processes, might play a key role, in the produced water treatment in order, to reject, let's say, some of the oil droplets, with 10 and above, let's say, micrometers. Membrane technology is a very wide, let's say, field of science. So there are so many rooms, to do research in this area. So, for example, you have researchers, focus on the on working with polymeric membranes. Others prefer, ceramic membranes. There are rooms also, for developing new membranes, as highlighted and indicated, by Dr. Roil, and this is where, I'm gonna throw in a few research studies, that were done by our group at Khalifa University, mixed matrix membranes as well, incorporating, nanotechnology, nanomaterial, in order, to tackle the several issues, associated with the treatment of produced water. So this study here, I'm going to take you through, and I will not go too much into the technical aspects, of these research studies, but I invite you, to some of them are published already, others are still under review. So they haven't been published yet. But if you need more information, more details, I invite you, to go through these papers, and I'll be happy, to also, discuss with you any interest, offline as well, or you're very welcome to share or to send me an email, and I'll be more than happy, to respond to your questions. So this study here basically is the preparation of titanium oxide silica ceramic membranes via dip coating for the treatment of produced water. It was developed by our ex-master student, Sarah. The work was published in Chemisphere. So I'll take you through very quickly, what we've done in this work is basically we wanted to synthesize TiO2, SiO2 ceramic membranes through dip coating method. And in membrane fabrication, I don't think it, we'll have enough time to go through all these very interesting, very fascinating, subjects, especially for the young researchers. In membrane fabrication, you've got several methods that you can deal with, starting with dip coating, to phase inversion, to electrospinning, to interfacial polymerization, and so on and so forth. So you've got plenty of these techniques, that you can play with in order to engineer and design, your membrane the way you wish, according to the a specific, let's say, type of pollutants, that you would like to reject or capture or remove, from your aqueous solution. So basically here we used the commercial ceramic membrane with 1 kilo Dalton. It was a TiO2 based ceramic membrane. And then we followed, the dip coating method. Basically, we prepared, several solutions, silica solutions at different concentrations, as you can see, from 0.25 wet% all the way to 1 wet%. And after that, we placed the ceramic membranes in these solutions for 26 hours. Then oven dried at 40 degrees Celsius for 8 hours, and finally calcinated. So as you can see, from the picture, that the final let's say ceramic membranes, coated with silica. We have used, advanced characterization tools such as, SEM, EDS, FTIR, Raman, and so on. We did, a whole bunch of performance tests. In order to understand and stand on the performance of these membranes after coating. So we wanted to study the impact, of coating these ceramic membranes with silica. So basically, these are the performance results. So you can see, control is basically a pristine membrane that does not have or was not coated with silica compared to the other concentrations, of silica used in this study. And you can see, the variation going up and down. So basically, we enhanced, the water flux significantly, by coating the ceramic membrane with silica. Apparently, we generated or we fabricated, hydrophilic or superhydrophilic membranes, and that was evident, by the contact angle measurements or analysis. And here is the SEM, microscopy images to see the surface morphology, of the membrane, because you wanted to understand, what's happening to the surface of the membrane after incorporating it with or coating it, with a new material. You wanted to see the changes, you wanted to see the surface roughness, and so on. So what's happening, because this is very, very important, especially when it comes to understanding the removal mechanisms, of your pollutant, basically. Do you have any adsorption? Do you have any electrostatic repulsion? So you wanted to see the surface morphology. And these are the cross-sectional images. And once again, cross-section when compared to surface, images, very important, because at cross-section, you wanted to see the channels, you wanted to see the water path. So you wanted to see the water flux, how is it going? And if you are really creating, some good channels, for water to pass through. EDS analysis, so we do that in order to understand the elemental mapping on the surface of the membrane. So basically, you get your membrane and you do EDS on the surface. So here we wanted to confirm if if silica, was present, on the surface, of these ceramic membranes or not. And from the EDS analysis, we could see some of the silica deposited on the membrane. So that tells us that, that our membrane has been coated in order to confirm, the attachment of the silica nanoparticles onto the surface of the membrane. So we've done, further analysis, FTIR, Raman, and so on. So all of these, supported all of the results, supported each other, and we could see some peaks, representing silica, indicating, the successful attachment on the membrane surface. In terms of yes,
we have 5 minutes, so if you want to skip all details, please.
Okay, all right. So so here is the performance test. So from that, we could see that there is a significant removal efficiency of TOC, total organic carbon, which represents, the oil content and the wastewater. On the right side, you can see the properties of the produced water, and we have worked with a real oily wastewater, that was obtained from a local refinery in Abu Dhabi. And the next part, which I'm going to go very quickly. So here we replaced silica with alumina, so Al2O3, and we wanted to see, so we followed the same protocol. We calcinated, we did characterization, we tested on the flux, we tested on the contact angle. So we picked up, several SEM images, FTIR analysis, Raman, to understand the attachment of alumina on the surface of the membrane. In this work, this is a continuation on the TiO2 ceramic membrane, but in this case, we try to use or decorate, iron oxide Ag composite nanoparticles, on the surface of TiO2. And this work has been submitted, and it's still under review. So as I said, we wanted to do this via chemical attachment. So we prepared in-house, in-house, the iron oxide nanoparticle. Then we attached silver, or we decorate that, the AG, the silver on the iron oxide. And after that, we checked for the successful synthesis, of Fe3O4Ag through several characterization techniques. And after that, we dipped, the TiO2 ceramic membrane in the solution that has the Fe3O4Ag, and we use, TOS as a chemical crosslinker, in order to get our new membranes, as can be indicated, from the right hand side, picture. We also, tested and did, several SEM, EDX, FTIR analysis in order to understand some further characterization on the performance, on the pure water flux, on the produced water flux, on the COD rejection, which all indicated, the enhancement or the enhanced performance, of the TiO2 ceramic membrane after coating. We did also, post-filtration characterization in order to understand on the removal mechanism. So what's happening exactly, with our membranes. This work was also done, by our postdoc, Dr. Mustafa, on the development and the synthesis of nanofibers. So we went here and we used electrospinning technology in order, to synthesize polydopamine coated WO3 PVDF electrospun nanofibers. Once again, so we tested, several concentrations. We did these are the images, of the nanofibers that we obtained. We did also, characterization. So all in all, we do the same thing. So basically, we develop the material, we engineer our membrane, and then we test it pre and post filtration in order, to understand the removal mechanisms and to check the performance of these membranes. And here we did some PS, iron oxide composite membrane, and this is where, a new project involving KFUPM, my colleague, Dr. Hasan. So we will continue working on this. We tested the PS Fe2O3 nanocomposite membranes for the treatment of separation of oily wastewater. So once again, we tested the different concentrations. We did characterization to make sure or to ensure the successful attachment of these nanoparticles, not to leach out, from the membrane. This is some of the mechanisms, how these bind together, the polymer, the nanomaterial, a cross-linker, if we have a cross-linker, and so on. Some post images, some post-filtration, some zeta potential surface charge. We wanted to understand, do we have any electrostatic, forces, repulsion, or attraction forces. And lastly, we have this, the super hydrophobic iron oxide olylambene, in UF membranes for oil and water emulsion. Because, once again, are we looking into hydrophilic membranes? Are we looking into hydrophobic membranes? Do we need to really pass water? Do we really need to pass oil? And all of these, decide or judge, on the approach that we will that we follow. So this is a very, very interesting concept. So we haven't published this yet, but we are shifting, towards biodegradable membranes, eco-friendly green membranes, and this is one of the biopolymers that we use is polylactic acid. So we functionalize, polylactic acid with oleamine iron oxide nanocomposite. We study, and as you can see from the picture here, how the hydrophobicity, of the solution or of the material that we used. So once again, we did, several characterization testing in order to understand on the performance, of the membrane that we developed. And lastly, very quickly, and this is in accordance with the integrated systems that Professor Cath, talked about, and I totally agree with him. So this is basically, we tried, to combine 3 different technologies into one. So we used ozonation as advanced oxidation process, electrocoagulation, as well as, the membrane, ceramic membranes, for the treatment of oily wastewater. So we've got this combination. This is very interesting piece of work. So we did it, in batch reactors as well as in continuous reactor. where we used to supply, oxygen instead of radiation. So we did a whole bunch of analysis, a whole bunch of characterization, even on the electrode deposits, afterwards to understand, the changes happening or the removal mechanisms, associated with the 3 different technologies. In one, I invite you, to go through these papers. Hopefully you find them helpful. And at the end, I would like to acknowledge all the research team, my students, my postdocs, my research staff, and also Khalifa University, for the research funding and for the continuous support. And once again, I thank KFUPM, Dr. Hasan, your team, and all the audience. Thank you so much.
Thank you very much, Dr. Shadi. Very interesting work. We have questions right there. Dr. Nadeem.
Yes, I think I am unmute. Yes, Dr. Shadi, yes, thank you very much for your nice presentation and talk. It is really interesting and very close to us what we are working here also. So it is really nice. I am Dr. Nadeem Bek and working as a research scientist 3 in IRC Membrane and Water Security Center. So I have a very simple question that is, that the membrane fouling is one of the major challenge, and most of the researchers and the scientists are busy in fixing this problem. So what do you think, which membrane is more suitable, like the ceramic membrane or the polymeric membrane? What actually can solve the problem of oily wastewater? What do you think is the better to go with it?
That's a very tricky question, and the answer to that also tricky, because you have let's say you have some groups, as I said, they prefer to defend, let's say, polymeric membranes, others defend, ceramic membranes. But my personal perspective and opinion, it all depends on the way you engineer and you design your own membrane. So the chemistry behind, let's say, the membrane development, I think plays, a pivotal role, in this regard. So first of all, you need to understand, the major foulants, that you're dealing with, and based on that, you need to go and capture, some, let's say, I would use this term antibiotics, right? So you need to understand, the material that can overcome, that major phenomena that is happening. Do you have any organic fouling? Do you have inorganic fouling? Do you have biofouling? So what kind of fouling do you have? And what in the inorganic fouling, what in the organic fouling, that you're dealing with? And based on that, you can develop whether now ceramic or polymeric. The other question is basically the cost. So which one is going to be, cheaper for you? Which one is going to be more practical, to your application on the long term? As I mentioned, at the end of my presentation, I talked about shifting towards, biodegradable membranes. So that's another area, I think is gonna come out very soon. There isn't a lot of researchers around the world, focusing on this. But I think, many of us have started this, and I think it's gonna perhaps, attract some researchers, very soon. But the bottom line is basically, I would say you can design, you can engineer your membrane the way you wish, if you understand what you're dealing with.
Yes, thank you.
Thank you.
I had a question, but I think I lost it, from Dr. Dawood. He was asking about the mechanism of oil rejection while making the surface hydrophilic.
Mm-hmm. Okay, so once again, the mechanisms, generally speaking, in membranes, we look at the size exclusion. We look at the let's say at the absorption effects, and we look at the surface charge, effects as well. So by making the let's say the membrane more hydrophilic, I would relate that into water flux. But in terms of rejection, the removal mechanisms, I would rely more, on the rely more on the 3 phenomena, that happen in the membrane. So we need to check from the properties and the characterization that we do on the membrane surface. And based on that, we can decide which mechanism, or perhaps, you have more than, you have maybe dual impact, of different phenomena, that happening in your process.
Okay, thank you. My question for the panelists, we talked about the challenges and the produced water treatment. So how about the opportunities? Is there any opportunity? Can you see any opportunity, Dr. Cath?
I don't know how to answer this question. I think, a few things bother me lately. One of the things that I hear, that I can hear here in the US, is that there's so much talk about renewables that people say, oh, produced water is not, it's not large quantities. Soon we won't have this problem, so that we don't have to do research. And I think it's absolutely wrong. I have the great opportunity to deal with other waste streams from other industries, mining industry, paper and pulp industry, metal industry. And sometimes I say, their wastewater is even more challenging than produced water. And I think, from the academic standpoint and from the industrial standpoint, if we know how to solve challenges in one field, we'll know how to solve challenges in other fields. And let's say that one day oil and gas will disappear and we won't depend on oil and gas. I don't think that we are going to escape from mining. We will need mining, metals, different things that we are mining from the earth. And there are big challenges for treatment of water, wastewater there too. So I think that's important to know. I think there are opportunities, and it's a regional issue. What do you do if you have too much water, or in what you do when you don't have too much water? So, I met with a company that developed a very unique evaporator system, and they developed it apparently mainly for the oil and gas initially. It's a very innovative sort of cooling tower that create the vortices of air inside, really cool stuff. And I'm asking myself, okay, so you're evaporating the water, why won't you capture it? So it's a concentration process, it's not water treatment process. And the guy told me, yes, but there are places that they have too much water and they don't know what to do with, so you do want to concentrate it and get rid of the water. But again, it doesn't help places where they don't have water and they need water for the next fracking or for the next operation. So I think that there are potential for implementation, and of course the price has to go down, because at the end of the day, the oil and gas business is like every business. You have to survive economically if you want to survive physically, and we have to reduce the cost of water. I think another things that I see, especially around the NAWI environment, people are pushing away the distillation processes, the thermal processes, in favor of more membrane processes. Again, I grew up academically as a membrane membrane scientist. I think membranes are cool, but membranes will always be more expensive, I think, than other simple processes. I don't know if they'll be more expensive than distillation, but if we can improve distillation to do a lot of heat recovery and heat reuse, in integrated systems, we'll do better. But we cannot escape dealing with thermal processes. Again, membrane distillation can be one of the places where you are combining thermal with membranes. But again, as others said, there are still many challenges there with hydrophobicity of the membrane, loss of hydrophobicity, fouling, a major issue. So it will be still the combination of good pre-treatment with desalination.
Yeah, thank you. Dr. Bilad, how do you see this dilemma? For example, Saudi Arabia is one of the most stressful country in terms of water stress. At the same time, one of the largest oil producers and one of the largest associated water producers. Do you see opportunity right here?
Okay, it's a tough question. Policy related. I think to look into produced water and resources is a little bit too far. I would think desalination using RO will be the golden choice over there. To think about produced water and consider that as resources to supply the water, that's too far. The opportunity, I think, is there, especially with the, I think, more stringent regulation. Especially, I don't know exactly in Saudi Arabia, but countries around here, Southeast Asia, they start to talk about lowering the standard for oil. The oil concentration below 10 ppm. Actually, a few companies approaches me, try to think about what they can do with that, because when the regulation is implemented, they will be in trouble. I think most of the onshore oil platform now that just use the simple things, descending and the oiling, to treat the produced water and just discharge to the sea, because the regulation is very soft in that process. Another big issue and opportunity, I think, is on they have a micron-sized sand that escape the descending. It goes through the final treatment process, and they have a problem in separating the sand, which I believe will become a piece of cake if we deal with the membrane. So I see big opportunity on the pressure-driven ultrafiltration, microfiltration over there. Especially when we take into account the substantial depletion of cost. Actually, membrane cost is very low, I think, compared to 10 or 20 years ago currently. So that will make the membrane very competitive and try to offset quite high costs associated with produced water. I just know the number now, close to $5 per barrel of water. Yeah, that's quite high. Nice to know. I think that's my view.
Yeah, thank you. Last question for Dr. Shadi. Dr. Shadi, you mentioned in the first slide that water is much more important than oil in UAE. So how do you see the opportunities for, make an industry for produced water in UAE? You are muted.
Okay, so I think from my perspective is that I think the attention is there, in terms of water, let's say water innovation, especially in the UAE. I'll give a very good example. The UAE, is the second largest producer in desalination after Saudi Arabia with 17%, total share, right? And they use MSF, MED, thermal desalination to get, fresh water. But currently they are building the largest RO plant in the world. So there is a shift, I believe, from thermal desalination into membrane, desalination process in the next, let's say, in the near future. So that perhaps, opens, let's say, room for membrane technology, development and membrane processes, in the field of produced water. So why produced water? So I think also the country, considering, the increasing the recycling ratio, the reuse ratio to 95% instead of 51%, that will also, let's say, be implemented, in the oil and gas industry. So they will perhaps, be in that situation where the stringent, regulations will come in place, certainly, at some point. In addition, the zero liquid discharge, that we're trying to do here or implement, in the UAE as well. So instead of discharging produced water into the Gulf, they encourage to recycle it, reuse it in situ, for several applications. So I think the future is there. Numbers, the market, the industry, the industrial market, the figures, even these scientific publications, as I showed, in the figure, everything is progressing quite well recently, and I think the progress will stay in this direction.
Okay, thank you very much. Any comment from our panelists before we end this webinar?
And I think just to add to Dr. Shadi on transitioning to membranes again, and I'm not doing much in distillation, other than membrane distillation, but again, one of the big questions in distillation in membrane process like reverse osmosis is the limited recovery because of the salinity. Using the current infrastructure and distillation infrastructure to deal with the brine, I think that will be the silver bullet. That will solve both the front end of cheaper desalination with membranes, followed by cheaper and existing infrastructure for brine management, and that's the solution to another solution to reducing the price.
Exactly, and this is in accordance with brine management, because even here in the UAE, they're coming up with many efforts in order to let's say to handle the brine rather than just disposing it into the marine. Especially the Gulf, we don't have, let's say, large surface water, so this is like a small gulf that we have with a small or a narrow opening to the Indian Ocean. So dilution is a solution concept does not really work. So over time it accumulates and builds up. So so they're considering now recovering some precious metals, turning brine into some valuable added products, recovering energy through PRO, stuff like that. They're discussing that on the table, and they are promoting innovation, as I said. So I can see it coming in the near future.
Yeah, and I think one of the things that again, in some circles we talk about it, brine management is something that you cannot ignore. It's a major issue.
Absolutely.
When we did the road mapping for the oil and gas industry under NAWI, when we talked to the oil and gas company and we asked the question, so what about zero liquid discharge, ZLD?
Right.
Nobody wants to talk about ZLD, because when you do ZLD now, so now everybody moved into moving produced water through pipelines. If you're going back into ZLD, you need to bring back the trucks and the trains and everything. And when you do the mass balance, you figure out that you'll generate mountains of salt. Correct. And the salt needs to go somewhere. So yeah, right. If you put the big mountain of salt, it's okay. You probably go back into sources, but again, sending it to the ocean is not a bad thing. Probably sending it back to deep formations that are already contaminated. That's probably a solution. But again, we're doing a very unnatural thing, and we need to figure out all the solutions for the the implications of it.
Yeah.
Okay. Well, thank you very much. It was a very nice evening, very informative, and we appreciate the time that you have spent with us. It is 12 in the morning, maybe in Brunei right now, and we are sorry for this, and we are.
It's okay. I used to wake late.
It's okay. We appreciate the time that you spent with us, Dr. Bilad. I would like to thank Dr. Tzhani Cath and Dr. Shadi, Dr. Mohammed Bilad, for being with us this evening and this morning, Dr. Cath. And we wish to see you again. The research and produced water will not stop, and we hope that we will see you again, maybe in collaborative work in the future. I would like to thank also the audience who were with us these 2 hours and a half. We appreciate it. We appreciate the support from KFUPM. We appreciate the organization efforts from Dr. Yassine, Dr. Dahiru. Thank you all very much, and have a good day and have a good night. Thank you.
Thank you very much. Thank you,
Bye-bye.
Hasan. Thank you.
Thank you.
Bye-bye.
Bye-bye.
Bye-bye.